Welcome to the Cognitive Informatics Seminar. I'm going to introduce Professor Lebière in French, and then he will speak in English. C'est pas la première fois que Christian Lebière se retrouve à Montréal. Je viens d'apprendre, et on est content de l'accueillir. Il est chercheur à l'université Carnegie Mellon. Il travaille sur les architectures cognitives et leur application à la psychologie, l'intelligence artificielle, l'interaction homme-machine, la prise de décision, les agents intelligents, la science des réseaux, la robotique cognitive et l'ingénierie neuromorphique. Donc, avec plaisir, je cède le volant à Christian qui va parler des architectures cognitives et leur application, cognitive architectures and their applications. Christian, it's yours.
So first, I must apologize for not giving this presentation in French. My technical French is not very good. Of course, if you ask questions in French, I will understand them, and I might even try to reply to them in French as well. And in general, as Stephen and I discussed, feel free to ask questions either in the, I guess in the chat. However Stephen wants to handle that, I'm happy to be interrupted rather than to give a straight lecture and then take questions afterwards.
C'est plus intéressant. It's more interesting if you ask questions, relevant questions during the talk. I'll transmit them to Christian.
So today I will try to give you as broad a perspective as possible on the idea of cognitive architectures and the kind of applications that they enable nowadays. The idea of cognitive architectures arose about 50 years ago that Newell proposed in his famous "You Can't Play 20 Questions with Nature and Win," the idea that to make progress on an understanding of the human mind as a whole, rather than the divide and conquer approach that was adopted in cognitive science at the time, that you needed some common framework. The theoretical framework was called Unified Theories of Cognition, and their computational implementation were called cognitive architectures. The idea of representing the basic capabilities of the human mind and the human brain in formal computational form and being able to deploy them as computer programs. A number of architectures have been proposed. Today, I will mostly talk in the context of a specific one I've been associated with, the ACTAR cognitive architecture. The current version of the architecture is illustrated on the right. As you can see, it's very modular, and we'll talk about sort of the mapping to brain areas later in the talk, but it's certainly we want an account of the human brain as well as the human mind. So there need to be some associations of those components of the architecture to the specific brain regions. And the component of the architectures, and again, we'll talk about that later, are fairly intuitive, right? You have the long-term memory, declarative memory, you have a central module for action selection, represented as production rules. You have a set of buffers that provide an interaction between those modules, memory, perception, auditory, manual command, etc., with the central production system. So that provides a constrained framework from which to model human cognition. Under the hood, even though the representations of knowledge and skills are symbolic, there is statistical calculus in terms of activations, in terms of utilities. You can think of it as Bayesian, you can think of it as reinforcement learning, that tunes those symbolic structures to the structure of the environment and then optimizes and continuously adapts the operations of the model. I think I'll give some ideas. It's not a normative architecture. It allows you to represent individual differences, cognitive biases, and those kind of things. And obviously, we're very interested in accounting for learning processes and training effects. One of the very early applications of cognitive architectures were to intelligent tutoring systems by providing a model of the learning students that could be used to optimize interventions. And you can ask some questions about cognitive architectures. Since they claim to be a unified theory, how predictive are they really? Can they account for individual performance, as we know that human behavior is infinitely variable? From a practical purpose, can they guide human-machine interaction? Can they be used to better understand artificial intelligence, other humans, and drive explanations? And finally, the bulk of the talk will be in the context of the ACTA cognitive architecture, but you can ask if there is a broader scientific consensus that's emerging about cognitive architectures. And the talk will attempt to answer some of those questions and illustrate some of those ideas. So the first part is I'm a computer scientist by training, and although I've been in the psychology department for the bulk of my career, I still think of applications as an important constraint on theories of cognition, not just a kind of experimental evidence gathered in cognitive psychology that we have certainly validated the mechanism of the architecture against, but also facing the complexity of the real world in terms of applications. And one domain that is increasingly popular for applying cognitive techniques is cybersecurity, which is a major practical problem given the ubiquitous nature of the internet and even the Internet of Things that control a lot of our physical world. So in that context, we have a project that is focused on cyber deception, the idea that a way of defending our computer systems is to deceive attackers in not attacking our systems. And obviously, you can see that the one principled way of optimizing a deception scheme against cyber attackers is to have a model, a cognitive model of the attackers that is able to derive a better way, not just optimal in general terms, but even personalized to the individual attacker. So that's the framework of this research, and the particular paradigm that we used. And our collaborator in this domain was Milind Tambe, who's currently at Harvard University, and who's very well known in game theory, and especially he made significant contribution to the idea of Stackelberg games for security. And Stackelberg games is a paradigm in which the strategy of the defender is known, perhaps through probing by the attackers. The attackers have a lot of information on the defenses, and then they can make their decision. So that's the case here, where, so you can see here is how the experimental view, because we run human experiments, we want to validate our models against actual human performance. So you can see here the view that the subjects were given. Yeah, that's a representation here that's supposed to be an insider attack at the center. And the 6 computer targets are around the periphery. And every target is characterized by effectively a payoff in terms of gold stars on a scale of 1 to 10, a potential penalty for being caught, those are the red stars, and a probability that this particular computer is being monitored by a human defender. And if the attacker attacks that computer, they will be caught and will endure that penalty. Otherwise, if it's not monitored and they decide to attack, they will gain the payoff here in terms of gold stars. The probability of monitoring that you can see is different from every computer has been optimized according to game theory to effectively even out the expected value of attacking each of these computers. So in practice, in average, 2 out of 6 are covered at any one point in time. And the idea of this paradigm is that you want to tell the attacker sometimes that a computer is covered, and you want to have essentially a mix in that warning of truth. You actually want to sometimes reveal that that they're covered when they're actually covered. Because you want also the deception to be plausible, you also want to tell them that they're covered when they're not covered. That is effectively a way, since you can only cover them, protect them 1/3 of the time, you essentially want to use a warning that expands that coverage through deceptive means. So the warning takes the form after the attacker selects one of these targets. They're given this warning here that the computer is monitored, and then they can either proceed with the attack and take their chances, or decide to withdraw and they don't gain or lose anything. The structure of the experiment is 100 trials over 4 blocks of different targets. So that's a repeated experiment in which the subjects can gain some experience with the system. So the cognitive architecture gives you a computational framework, a structure, a theory for how people behave. It does not actually tell you how people actually behave, no more than you can take a baby and put them in front of a computer and have them do anything useful. So the cognitive architecture is a framework in which to develop specific models of tasks. Now that's potentially a problem, because developing those models can be that represent skills and knowledge used in those tasks can be very time consuming. And from a theoretical point of view, it can also create degrees of freedom in terms of choosing particular strategies or particular sets of knowledge. One approach that we've used to try and alleviate both those practical and theoretical problems is to adopt a methodology called instance-based learning. That's basically based on the idea that people make decisions in real life, not based on some predefined strategies, especially in domains for which they have no experience. Rather, they make decisions based on the experience. So that essentially creates a process where they make decisions based on the experience. They gain additional experience through those decisions and the outcomes. The cognitive architecture and the model is able to learn from them and repeat. An attraction of that approach is that it is strongly constrained by the mechanism of the cognitive architectures. And there's an illustration of the right here for this particular case, where an instance, an experience with this paradigm is represented. You have a context of the decision. And here, that's to represent each particular choice, in this case, each target, in terms of the features that are provided for that target. So as we saw, those are composed of the reward, the payoff for a successful attack, the penalty for an unsuccessful attack, and the monitoring probability. And the way the model works, essentially for each potential action, which in this case are to attack or not to attack, to generate an expected outcome for that action, and essentially choose the action with the best expected outcome. The way those outcomes are generated, and it's essentially a consensus outcome that reflects not one particular experience, but the sum of all experience, a generalization, is determined by the mechanism of the cognitive architecture. And since those instances, those experiences are stored in long-term memory, those are in particular the activation calculus in memory that represents the statistics of the experience, of the memory, the knowledge in memory. Very briefly, there is that concept of activation that is composed on 2 terms. It's essentially, you can think of it in Bayesian terms, of a prior that here represents the power law of practice and the power law of forgetting, that are overwhelming phenomena in human cognition. And then a partial matching term that depend on similarities of the feature values, that essentially you can think of it, if you're familiar with neural networks, of generalization from distributed representation. There is a noise term, so the process is stochastic. You don't always retrieve the same memory in the same situation, and which memory you retrieve will follow a Boltzmann distribution, with the more active memories being more likely. And to generate this kind of consensus expectation, there is that formula for a mechanism that we call blending, which is essentially a weighted consensus of all the memories, again, according to those similarities, in this case, the similarities in the outcome space. So that gives you a very general mechanism that can be used to make decisions. We've applied it to dozens of domains. It requires very little from the modeler other than effectively specifying the representation of the instances and the decision rule, which in this case, as we saw, are very basic. And then it leverages the mechanism of the cognitive architecture, the learning, adaptivity, generalization, and so forth. So as I mentioned, just to repeat this, the process is really straightforward. In this case, the model evaluates each target in succession, generates an expected outcome for them, select the target with the highest projected value based on the experience. Then they receive a signal, and then based on that signal, they revise the expectation for this particular target. If it's still positive, they decide to attack. If it's less than 0, they decide to withdraw, because withdrawing has an outcome of 0. So that's a very simple, very constrained model of the task. And we see here that that's a representation of the results compared to human performance. So the black lines is the human performance, and we run an experiment. I showed you what it looked like with 100 subjects on the mechanical Turk online. So that's an easy way to get a fairly large number of subjects. And you have in gray the performance of the model. As I mentioned, there are 100 trials organized in 4 rounds of 25 trials. Each round contains the same set of targets, so people can get experience with each target and then to choose whichever one they think is best and repeat that. And then they get other kind of targets with this different distribution, so they have to generalize that. You can see on the left here, that's the presentation of the model, the probability of attack, which was our main performance measure, comparison of the human and the model. And you can see that the model does a very good job at reproducing both the general probability of attack as well as the trial-to-trial sensitivity in those. It's actually quite a very impressive fit to the data. On the right, you can see the distribution of probability of attack across those 100 subjects. On the left is the average probability for the 100 subjects. Here, that's the distribution over all trials of the overall probability of attack. And you can see you have a huge range of human performance, from almost half the subjects who attack all the time, who decide, you can think of it as reckless, but they think of it as being worth it. And it turns out that they still have a positive expected value by attacking all the time, because you only have 2 defenders for 6 targets. All the way to subjects who barely attack much, who attack maybe a quarter or more of the time. And you can see that we do the same thing, just like we run 100 subjects, we run the model 100 times. I mentioned that the model learns from its own experience, that the process of leveraging that experience is stochastic. So it turns out that you have a process there that reflects the experiences. And if a model is particularly lucky early on, then it will go on and attack a lot of the time. If it's unlucky, then it may conclude from its experience that the expected value are poor, so it will shy from attacking, except in some cases. So you can see that the distribution over models very closely matches the distribution over humans. So not only can we reproduce average human performance, which is sort of the bread and butter of cognitive models, but we can also reproduce the distribution of behavior across humans based on their learning experience. Now I have a confession to make. Usually the standard practice is that people collect the data, then they develop their model, and they may fit the model, whether that's parameters, whether that's model design, to the data. We did not do that. Instead, we designed the model and ran the model before we collected the data, and we published it. And this is sort of what our original model was, in terms of that the distribution of probability of attacks that I showed on the right previously. And it's not a bad fit to the range of human performance, but it was really missing that large percentage of subjects here who attack all the time. The model was just never that reckless. And it turns out that we had, I guess, outsmarted ourselves a little bit. So the process that I described of instance-based learning, of generating expectations from experience, generates a piece of knowledge there. You're conscious that you say, well, okay, this is probably going to go fairly well, or this is going to go very poorly. But we decided we were not going to represent those in memory, even though they're actually created. Rather, we were just going to represent the experiences in memory. And it turns out when we remove that sort of artificial eraser of those pieces of knowledge, so that now your experience is a mix of your actual experience, of the outcome of your actual decisions, together with your expectations. You saw in the previous one that now you have the model can recreate also that large proportion of subjects, that then the explanation is that they're lucky early and they keep generating positive expectations. Even if the expectations are then disappointed, that is essentially a wash because you generate a new expectation for every disappointed experience. So that's effectively an account of confirmation bias. And in past research, we've shown that the cognitive architecture can account for a lot of the cognitive biases that have been proposed and observed in the decision-making literature. And just like this one, those are essentially consequences of the mechanism of the architecture and the flow of information. Once we sort of got rid of that and then corrected a couple other things, and that's the importance of really putting the model in the same situations as the humans are, because the details really matter, then we got the kind of fit that we observed. But doing that kind of predictive modeling, not just post hoc modeling of the data, is, I think, a really important process for testing theories and determining what is really useful in accounting for the data. So now that we had that model, that would allow us to put them to the test. And for example, what you want to do is say, okay, we had a particular signaling scheme here that was driven by that Stackelberg game theory setting. Now, what if we generate different deceptive scheme? And we saw in particular that deceptive scheme to be, but subjects still attack 75% of the time. So we started generating more deceptive schemes, more computational schemes by which the deceptive signal was generated, and testing them, against the model, generating predictions for the model before we ran the human subjects. And you can see here, so this was the original one in red. We gave a variant of the scheme where the subjects, when they received the warning scheme, were given the explicit probability that the signal was deceptive. As you can see, it didn't change performance much. And then we run them against a setting where no warning was given. And you can see again that the model does a very good job at recreating the distribution. We had a number of other deceptive warning schemes, and every time the model was able to do a very good job in predicting how humans would react as compared to the actual human data in advance. So that's an application of cognitive model here, of sort of in the education domain that has been called synthetic student. The idea that once you have a model, in that case of the student learning, you can test various proposed educational schemes and determine the effectiveness before you actually test them on actual students. So that view, that those are a couple of those other schemes here that were driven by some other machine learning paradigms than the Stackelberg game theory. And you can see that in every case, the model does a very good job at accounting for the variations in human responses to that. Now, what we've done up to now is compare distributions. We've seen that the model, we run the model 100 times compared to the 100 human subject. We can see that they fit the distribution. But you can ask yourself, well, can I actually match each model run to a specific human subject? And we can do that. There is a methodology that was initially developed for intelligent tutoring systems called knowledge tracing, which is essentially forcing the model to make the same decisions as the human. So they align the experience with it, and gradually they develop the same experience. Since we saw that the model performance decisions were based on the experience, now we have the model sharing the same knowledge base at that particular subject. When you do that, you can see that the model probability of attack matches very closely. That's an extremely strong correlation there at the individual level. So each red dot is a human subject, and with the, on the y-axis, the probability of attack of that model that follows the human subject, each time predicts the action, but then is forced to do the same action as the human, so they share the same knowledge base. So you can see that this is a very effective way of taking a general model that will learn from experience, force it to follow the actual decisions of a human, and every time predicts the next decision of that human. Now, one thing that we can do with that is use the model then, instead of relying on AI algorithms like game theory or machine learning to drive the deceptive signal. You can personalize the signal to that particular model that you've aligned against the experience and the behavior of that particular human attacker. You could do that by running the model in Monte Carlo mode and make predictions, sort of forward, look ahead, and so on. Here, it turns out that the instance-based learning approach, and we'll see more demonstration of that later, allows you to introspect in the model and essentially approximate the behavior of the model through various equations, and then use these equations to optimize the signal. That's what we did. So then we played the game. Let's say we're going to run 100 new subjects against the model, which now adapts the signal. And we had predictions of what and the model essentially has blocks of signals that they decide would be deceptive or would be truthful. And our results were initially disappointing. You can see here in blue, the human behavior. Well, in black is the original behavior that we saw against that game theory algorithm. And in blue was the human behavior against our cognitive signaling algorithm versus the predictions of the model in yellow there. So we were disappointed, but then we started looking at the data. And fortunately, we'd given the subjects afterwards a questionnaire that essentially asked them what they paid attention to, what they based their decision on. And it turns out that and we split that in between the humans that attack almost all the time and those that attack less than all the time. And it turns out that a large proportion of the humans that attack all the time had just decided to ignore the signal. So what we did was to create a different version of the model that did not represent the signal at all. And now we had two versions of the model, one that the original one that paid attention to the signal and the new one that does not. And we matched each version of the model against a group of subjects. And you can see now that we have a very, very good match of each version of the model against each group of subjects. So that's a little bit of a cautionary tale, of course, that human behavior is always variable. We have some theories about why those subjects decided to stop paying attention to the model, but we had to account it in this particular way, even though we could conceptually account for it by having the model itself learn whether it's worth paying attention to the signal or not. So I'm done with the first part of my presentation. I think there was a lot of laying of the ground here. I'll go faster in the other ones, but maybe now would be a good time for taking some questions.
Well, I put one in. It may be based on my misunderstanding of your method, but I was thinking that if predictive modeling, well, you can see it in the chat. If predictive modeling is more useful than the alternative, which is to give me the alternative predictive.
Right. Well, the alternative is to do post hoc modeling, right? So predictive modeling, I think, is very useful both from a theoretical perspective of learning what you can account for out of the box, if you will. And from a practical point of view, because in the real world, you often don't have the luxury of collecting the data and fitting your model to it. You have to predict things sort of without a net, if you will. But certainly there's always the case human cognition is very variable. So in this case, we learned that there was sort of we should have accounted for that confirmation bias that we could have, but we decided not to in the original model. So sometimes modelers make mistakes, right? So you have to do some post hoc modeling to sort of learn from the data and correct the mistakes. We're not at the case yet where we can do sort of 100% predictive modeling purely from a principled perspective. I mean, we have still some ways to go. We can go a long way, and then we don't depend on data. And that's a fundamental difference between sort of first principle modeling like this and machine learning. Machine learning needs the data. If machine learning doesn't have the data, it has nothing, right? Whereas we can make a very good first guess without having the data. And in general, cognitive modeling of our kind is much less data hungry than machine learning. But it's still a useful exercise to compare to data and correct your model when it doesn't account for all aspects of the data.
Okay, thank you. Are there any other questions at this point? Est-ce qu'il y a des questions à ce moment-là? D'accord, alors on continue, Christian, merci.
Yeah, merci. So another domain of application in which we applied cognitive model is explainable AI. And the need is prodded by the fact that a lot of the very successful AI algorithm that we have nowadays, especially machine learning algorithm, especially deep learning algorithm, are effectively opaque black boxes. And it's one thing to rely on them because their performance is pretty good, but especially in critical application, it would really be useful and beneficial to be able to understand why they're behaving the way they were. And so that came the idea of explainable AI. And our assumption is that explanation is fundamentally an interactive, an incremental process. It's not something that is just thrown out to the user, but it's really a dialogue between the system and the user. And from that perspective, modeling the user is a really critical capability because you need a theory of mind of the user, of what the user knows, what the user understands, in order to adapt the explanation interactively to the user. One size doesn't fit all. So there came the idea of modeling the learner itself, so whatever piece of AI, deep learner, think of it as a deep learner, and a human user in the same cognitive framework. And the idea there is that cognitive models provide a common ground between machine and human. On the human side, as we saw, they've been designed to represent human cognition. So they have that natural connection there, is that the model of the user is very much in terms that are cognitively meaningful to the user. And it turns out we showed in previous research that cognitive model can be essentially abstracted from especially from machine learning, connectionist networks, deep learners at a sort of a higher level of abstraction. So from a computational point of view, there is a pretty direct mapping there. So we have cognitive models at that middle ground, that common ground between human and learner to drive an explanation system. And in particular, the idea is that you have a dual model there, a process that compares the representation and the actions, the behavior of the machine. And that process of aligning that model against the machine is very much the same process that we saw here in terms of aligning against a human user. Essentially, you treat the behavior as a black box. And on the one hand, you have a model of the human as well, from their actions, from their interpretations, and you're going to drive explanation when you find discrepancies between those two models. So that's effectively what this graphic here. So you have, and again, as I mentioned, we'll use the same instance-based learning model that we described. So one basic choice is what are the features of the representation. On the human side, you can usually have access to a human ontology of whatever domain is at work, but you cannot guarantee that the deep learner has developed the same representation and the same ontology. So what we did there was use introspection into the deep learner to learn more about their representation. And the last thing that I'll mention is that on the right there is and we applied this to a UAV flight. So UAV are an inhabited air vehicle, so they're drones, if you will. And a typical sort of drone pilot follows this architecture there of a convolutional neural net that can be used to process both egocentric and allocentric representations. Then the elaboration of a common representation on top of that, then essentially a decision stage that is driven by reinforcement learning. And you can see there that potentially the levels of this deep learner correspond to different cognitive terms. So for example, if something gets misprocessed at the perceptual processing scheme, you can account for it in terms of attentional terms. If something doesn't get represented, as we'll see in that centralized sort of higher level representation, you can think of it as a categorization or representation error. And if the right decision isn't made, then you can explain to them in decision-making terms. So there is a general mapping there between those AI architectures and terms that would be cognitively meaningful to a human decision makers. And again, we have cognitive models, cognitive architectures as the common ground between these two worlds. So one thing that I mentioned, we'll use the same instance-based learning approach. But one thing that we did is introspect into that representation of the deep learner and use techniques like TSNE that are used for dimensionality reduction to understand the representation that was made of in the learner, and then represent the model representation of the learner in those particular terms. So now, once you have that representation in the model, you can use the same sort of abstraction that I described in the previous talk. So in that talk, that abstraction that was used to drive the cognitive signaling was framed in terms of the impact of interventions for future decision. Here, what we want to learn is how salient are the various features in the representation, because that's often the case where the deep learner and the humans are misaligned. The human has some features in mind that are really essential for making decisions. And we want to know if the learner has those same features, and in particular, whether they weigh those same features in their decisions to the same extent that the human does. So we developed a process called cognitive salience, which is similar to the visual salience. You may have seen some heat map visual processing. That's effectively the same way. It's a way of introspecting in the processes of the cognitive model and extract that information over how salient each feature is in this set of experiences in terms of driving decisions. So this was our first application. That's a very simple one, but that's very illuminating. So this was a very simple task in the game StarCraft. And that task is called the beacon task. You have an agent that is here, and the goal is to go to one of two beacons. Sometimes there are two beacons, sometimes there's just one. A very simple task. There is a green beacon and there is an orange beacon. And it turns out that one beacon is worth a lot more than the other. So you should go there, it should learn, the system should learn, and it does learn to prefer the more valuable beacon than the other one. And it's very simple. You just click on it and the agent will take a path to that. There was one problem with the deep learner, though, is that when the two beacons were aligned, for example, if you were to move the green beacon here, it would select the more valuable orange beacon, but then the agent would hit the green beacon first on its way and would sort of take the less valuable pair. And we were wondering why the deep learner would do that. When we introspected into its representation, we saw that it had been trained, again, on cases where you'd have one or the other or both. So when you just had the green beacon, there's the representation, again, in that dimensionality reduction of what was a 300 component vector. The orange one is when you just had the orange beacon. And the combination of red and pink is when you had both beacons. But you can see that the set of conditions where one beacon was exactly aligned so that it was blocking the other one overlap in representation. So the deep learner had not learned to make the distinctions, probably because it had not received enough instances of that particular case, particular blocking case. So it had not found it useful to make that distinction. So we saw here from our introspection that the reason why the deep learner was behaving in a suboptimal way was because that particular feature there of the blocking of one beacon blocking the other was not represented. So we were able to capture that in the model, use the human model to train the deep learner through its sort of model of provide a lot of more training so that it would learn that distinction and then in turn would improve that performance. So that's a case of explanation used for training and remediation. We have other domains, like we have an adversary task in grid world, where the humans learn a particular strategy for fooling the agent, the deep learning agent that controls a predator, and keep it away from the goal. And we were able to show again that the model can capture whether the deep learner has learned that particular strategy or not. Similarly, a slightly more complex domain here of navigating that UAV and different strategies for getting into a canyon. And so we tested our explanation against human user, and you can see that there is a benefit to the explanation. Now, one cost of explanation is that they take time to process, and you can see that that explanation, when corrected for the time on task, and in particular the extra time on task to process those explanations, is still beneficial, but it's less compelling. So that certainly, there is certainly a lot of work that can be done to improve explanations of AI and deep learning systems for human users. Now, we had developed those techniques, especially the cognitive salience technique, and it can apply to any cognitive model, in particular to any instance-based learning model. So what we did, we took that technique, took our previous model of cyber deception that I showed, and introspected into that model with that technique. Right off the bat, it didn't take any adjustment or anything. And what you can see here, so this is a triangular plot here. So again, each circle is a particular human user, and their point in this space depend on whether the salience of those three features, the payoff, the penalty, and the probability of monitoring, which feature that particular user was more salient from, and we extracted that from the model that was aligned against that particular user. And you can see that there's the differential sensitivity there. We Yellow are those that rely mostly on reward, blue those on probability, and red those on penalties. So you can be more sensitive to different aspects. So some people, for example, are very sensitive to penalty, so they shy away from the high penalty items, so are more driven by the payoff, and so on. So we were able to introspect in the model and understand what was driving each user by looking in the model that was aligned against that user. And that's a different representation there in terms of the individual targets and their characteristics. All right, so that was the end of the second part of the talk of how you can use cognitive models to drive explanation systems between AI and humans by essentially having models aligned against each side. Any questions of that? All right, so third part of the talk, that issue of trust in automation. So as we saw two cases here where we were injecting models in human-machine systems in various guises. So in one case, that was the model both as synthetic user and as a way to drive the algorithm for deception. In the second case, that were models that would drive explanation between human and machine. One key aspect of human-machine teaming and human automation integration is the issue of trust in automation. And in particular, in our case, can cognitive models account for the conditions in which humans decide whether to trust automation or not? And what drives that trust in automation? And while there are a number of theories of trust, our assumption was that the cognitive model, which is used for making decisions, can also provide some measures of trust through similar process of introspection that we saw before. So this particular paradigm here, again, we're in a UAV domain without going into too much detail. The human subject had to select a set of potential targets for the UAVs. Once over a target, that area of the map was significantly larger than what their camera would afford. So they had to look for the target within that area. So they had two choices on how to do that. One is to rely on automation that would provide a direction of the target within that area. You can see in the form of that red arrow. Or to rely on a human decision maker, a human commander, to provide that information. The difference between the two is that the automation provided that advice instantaneously, but was only correct some portion of the time, 70% of the time. Whereas the human commander was always correct, but took 5 seconds to give you that input. And the key aspect is that the automation was, the correctness of the automation depended on two features. One is the number of sensors on which the information, the data was based, and how old the data was. So those were the two features that determined the probability of correctness of the automation. And of course, the task was for the humans to learn when to rely on the automation versus when to rely on the human commander. In the cases where, based on those features, the human automation would be correct, it was more efficient to rely on the automation. In the cases where it was not, it made sense to rely on the human commander instead. So that's essentially, and there were two decision stages, just to make things a little bit more complex. You would have a decision stage where you would decide to get input either from the automation or the human commander. And then you had a second decision whether to rely on that advice or not. And that seems sort of fairly counterintuitive. Why would you ask for the advice if you were not going to rely on it? And it turns out that process is fairly complex. So there were some subjects, for example, that would decide to rely on the human commander, but not wait for the input, just start searching on their own. Or there were some subjects that decide to rely on the automation, but not trust the automation fully and decide to start exploring independently, regardless of what the automation said. So that was a two-stage decision there that we model, and the way we modeled it very much the same way, again, an instance-based learning model, very much sort of leveraging the cognitive architecture and putting as little as possible engineering into the model, trying to get predictions directly from the cognitive theory. So there were two outcomes really to this. One is so those are the two features, the number of sensors and the age of the data. The two actions, rely on the automation versus rely on the commander, and two outcomes. One was the total latency to find the target, because if the hint from the automation the commander was not correct, you would still have to search the whole area, and that would take more time, obviously. And the second one is whether the advice was reliable or not. So we use those two outcomes to drive the two stages of the decision. As we saw before, it would generate an expected latency, which is really the performance measure for human versus commander in those conditions, given those features, and would choose the option that gave the lowest latency. But then the second stage of deciding whether to rely or not was determined by generating an expectation of reliability. And if it was below some threshold, decide not to rely on it. It was above some threshold, decide to rely on it. Again, straightforward representation of the problem, all parameters at the default value of the architecture, and then generate predictions of the data. Without going into too much detail, I'm running out of time. These are performance of the human in light blue versus the model in dark blue across the decision stage and the search stage. So those two stages, two different measures of positive power and negative predictive power, so that think of it as signal detection. And so the bar is the averages for the subjects and the models. Again, we run the model a bunch of runs just like the subject. And the individual circles are the variability in human subjects and model. And you can see that generally there is a very good agreement, and also that the model variability matches the human variability as we saw in the other applications. Now, back to that issue of trust. So after the experiment, they asked the humans, well, how reliable was the automation? And they were able to introspect and give some sense there. And then we could do the same thing with the model to essentially have a context-free retrieval to say, oh, extract that reliability component out of each chunk and give me that consensus. And it turns out that both human and model were biased in the same way. They tended, so the actual reliability was 70%, as we saw. And you can see that humans in general and model tended to overstate that by 5 to 10%, as well as individual variability, where individual humans and individual models both over and underestimated. So we have a good match there. We have a good sense of both through the behavior, as well as through introspection, whether the human and the model trust the automation. And what we ended up doing, and I sent that paper, is what the model gives you is the ability to play a lot of what if I change this in the automation? What if I change this in the display? How will that affect trust? You can run a lot of these what if games very efficiently with a model, much more than you can with human subjects. All right, so the last part of my talk, wrapping up here, since I have a few minutes left, and you can ask, well, this is the ACT-R theory and the ACT-R cognitive architecture, and it looks pretty good, but there are other cognitive architectures, and we're 40 to 50 years since Alan Newell proposed that program. And they have a lot of architectures that have been proposed. And you can see here, John Tsotsos and colleague at the University of Toronto did an extensive survey of the first 40 years of cognitive architectures. Very nice work. And you can see here On the vertical axis is all the architectures that have been proposed with some timeline there and a color coding of which are active and so on and so forth. You can see Actar there, you can see SOAR, you can see Marcel Just CAPS architecture. And you can see there is a continuous process of new cognitive architectures being proposed and sometimes stopping activity or sometimes continuing. Now, you can also look at what aspects they capture, and those are sort of various cognitive functionality there: perception, action, selection, attention, motivation, memory, learning, etc., and so forth. And you have there, again, the architectures are listed, what component those architectures capture. And finally, you can look at the models that have been developed and the applications, and you have a list of potential applications here from psychology experiment, robotics, games and puzzles, computer vision, etc., etc. And you have, again, a categorization of what each architecture has been applied to. So that's a fairly active and very diverse set. And you can ask yourself, well, what are we to learn from this scientifically? Are they all disagreeing with each other? Is this adding up to anything? And it turns out, so myself and a number of colleagues, especially John Laird and Paul Rosenblum, who were instrumental in Newell's SOAR's architecture, and more recently a colleague, Andrea Stocco, came up on the realization that, you know, even though when you look at those architecture modules, and this is Actar here that you've seen, this is the current version of SOAR, and this is Paul Rosenblum's Signa architecture. Even though the form factor looks very different, they have really converged to at least a general consensus over what the components of human cognition are, of the unified theory of cognition are, and how they interact with each other. So the color coding here is meant to highlight the commonalities, and this is a representation of sort of a diagrammatic representation of the key modules and how they interact. And as well as a set of more specific assumptions about how each module, on which basis each module is working, what are the mechanisms, on what principles do they operate. And it does not come overnight, so we did here a little categorization, dimensionality reduction. We took all these assumptions and mapped Actar and SOAR circa 1993, and the three architectures that I showed, Actar, SOAR, and Sigma, right before we wrote that paper in 2016, and codified the level of agreement with what we stated as the consensus. And you can see there, and then the dimensionality reduction on this. And you can see that initially Actar and SOAR were actually quite separate and made very different assumptions early on in their history, but that they have really converged to a remarkable degree because you apply the architecture to a lot of domains and you learn the lessons. It's a slow process, it's a slow theoretical process, but it's an effective process. But you know, you can ask yourself, well, you know, you see the structure, it's sort of, yeah, maybe it's a little bit motherhood and apple pie, right? Yes, you have memory, you have working memory, you have procedural action selection and so on. Well, yeah, okay, we sort of know they're there, right? Isn't that intuitive? And it turns out not entirely. So one theoretical possibility that cognitive architectures give you, since, as I mentioned, they're meant to represent not just cognition in the abstract, but the working of the human brain, is to see whether that consensus, that common model of cognition, actually represents how the human brain is organized. So that's what my colleague Andrea Stocco did, which is there has already been a lot of work on mapping those various components over particular components of the human brain. What the common model of cognition gives you is a pattern of connection between those areas. So Andrea used a technique called dynamic causal modeling to analyze the flow of activation across the brain and compared that to the predictions of the common model. And he compared that to a number of competing proposed architectures or hierarchical systems, either closed or open, hub and spoke, either closed or open. And one of those, for example, has been proposed by Carl Friston, who I believe will be a later speaker in the seminar series. So it is not the case that that formulation of the common model is really something obvious, that everybody agrees with it. So now let's test it against data. Without getting into the detail of the statistics, there are two measures in terms of expected probability of exceedance probability. Andrea applied that, used the massive human connectome database of neuroimaging data over a number of tasks for thousands of participants, selected the more 6 out of the 7 tasks. The motor task was really not fully suitable, but he took the other 6 tasks and a wide range of human data, fMRI in particular, and tested the common model structure against those competing proposed architectures. And you can see here, so this is the measure, this is sort of the looser measure of expected probability, and in black is the common model, in gray are the other architectures, and the 6 graphics are the 6 different tasks. And you can see that generally the common model is the best model for each task of the flow of information across the brain between those areas. That's even clearer if you use the stricter measure of exceedance probability there, where it's a really compelling pattern. If you put all those tasks together, and again, this is expected probability on the left, exceedance probability of the right, it's clear that the common model is a better fit. And what you can do here is look at each connection separately and see how much they contribute to the fit. And in particular, on the right, bottom right here, you can see that really every component of the common model is necessary. It really is a full picture of the set of connections in cognition. So quick answers about those speculative questions I asked at the start, and you can read them. I think that cognitive architectures are predictive. We show that they can account for a pretty compelling range of individual performance. They can be used to guide human-machine interaction in a number of ways, as well as explanations. And really the most, I think, compelling and optimistic aspect of this is that there's really a broader scientific consensus emerging about how they capture the nature of human cognition and the structure of the human brain. Thank you.
Christian, thank you ever so much for a very stimulating and informative talk.